Right. Hey, I'm Michael Pratt. I'm a software engineer here at Google.
I'm Ben Barenblat. I'm also a software engineer here at Google.
And for the last year or so, we've been working on a side project to port the Go language to RV64G, and we wanted to come give you a quick update on what we've been working on and how it's been going. So for those of you who aren't aware, Go is a statically typed programming language. It was originally introduced by Google, a team at Google, in about 2009. Go 1.0 was released in 2012. And some of the goals of the Go language were to sort of meet some of the needs and fix some of the problems that teams had encountered at Google building large-scale software, typically in Java or C++. So the language has been kept intentionally fairly simple. It looks a little bit like C, so it could be productive and readable. It also has strong built-in features for concurrency and networking, as those tend to be very commonly used when building large software. It's also a garbage collected language. It has runtime and so on. And it's been getting growing popularity both in Google and in the wider open source community, particularly for sort of web backend servers and a fair amount of system software. For instance, if you've heard of the Docker project for Linux containers, that's written in Go, as well as a number of other projects. So why are we interested in RISC-V? From the Go perspective, we're interested in bringing Go to as many architectures as possible, which helps both the Go community and the RISC-V community, so we can get Go applications ported to RISC-V and Go developers able to develop their stuff for RISC-V cores. And in a more general sense, Google's been interested in additional alternative architectures to, say, Intel and ARM for quite a while. Google recently announced a server called Zeus, which is a Power 9 server in partnership with Rackspace, which is part of the Open Compute project, sort of expand this horizon, as well as Google's been interested in a variety of accelerators. We've got accelerators for speedy on machine learning and so on. And we're also very interested in open source, the OpenISA. We had a number of great talks yesterday about security, and I think RISC-V is in a great place to help move us forward in terms of computer security, so supporting that is great. So what do we need to do to support RISC-V on Go? Go has its own, official Go toolchain has its own standalone toolchain, mostly written in Go. There are GCC and LLVM frontends for Go, but the vast majority of Go software is built using the official Go toolchain, primarily because it supports the official Go runtime, which has the state-of-the-art garbage collector, the state-of-the-art concurrency support, and so on. So to support RISC-V, we need to add support to Go's compiler, its assembler, its linker, and its runtime. And one interesting thing about the Go toolchain is it actually has its own assembly language. So you can see here a comparison between Go assembly and what normal RISC-V assembly might look like. So the reason Go has its own assembler is mostly to support Go developers who are working with multiple architectures can do so without learning all the different assembly syntaxes. But all of those things are what we need to support and get working before we'll have Go programs working.
So we've been doing this for about a year. We've actually gotten pretty close to having a real working tool chain that you can use to actually compile Go programs. The assembler support is very good. The compiler and the linker are most of the way there. Our big blocker right now is the runtime. Anything that stresses the runtime too heavily just doesn't work yet. This is because the runtime doesn't compile. Now, fortunately, the runtime is written in Go, so most of getting the runtime to compile consists of going and banging on the compiler until it can compile the runtime. So that's what we've been doing for the last couple of months. That's what we're going to be doing for the next couple of months. We're optimistic that the runtime is going to compile within the next few months or so. In the meantime, you can actually compile and run, basic, relatively simple Go programs. If you've got something like this is a factorial program, we can actually go and write this. We can run it through the Go compiler, and we can run it under Spike, and it will actually do the right thing. So this has been very satisfying, actually seeing us get to the point where we can run real programs that we've written in Go. In general, working with the architecture has been great. RISC-V has been a fun architecture to work with. It's nice and orthogonal. There's usually one obvious way to do the things that we want to do. But really, the biggest win has been the open source model. The fact that we can go online to the RISC-V opcodes repository and go and clone the list of all of the encodings for RISC-V, and we can use that to auto-generate parts of the compiler, has been a huge win for us. It saves us a ton of time flipping through the architecture manual, trying to debug typos in the back-end generation. This has been great. By the way, whoever runs the opcodes repository, you should merge our pull request for Go support. Actually, the biggest gripe that we've had with RISC-V has just been that loading 64-bit constants is kind of a pain. It's obvious that you're intended to do this with a literal pool, but we're not quite ready to add that complexity to the compiler just yet. So right now, we're emitting up to 6 instructions to load a 64-bit immediate. So don't use 64-bit immediates. It's also important to note, this has been a community effort. We have not been working alone. We've had a lot of help from people like Josh Bleacher-Snyder, who is an upstream Go dev. Josh knows a lot about the Go compiler internals, much more than either of us does. And so having Josh be able to help us has been great. He's committed a lot of code, and he's really helped us understand what's going on inside this very complicated compiler system. We've also just been joined by Amal Bav, who is an MIT student. He's done some work synthesizing RISC-V cores using BlueSpec. He actually just started contributing a few weeks ago, but he's already contributed a ton of code, and we're really, really happy to have him along as well. We would love your help as well. Actually, a lot of our wish list items, people have already been talking about. You know, it would be great to have better documentation for the ELF ABI, for what relocations mean. It would be great to have more frequent releases of the GCC toolchain and Spike. And we have no silicon right now to test on, so get us some RV64 silicon that we can run Linux on so that we can try out Go. We've also been working pretty closely with the Go upstream developers to ensure that we don't diverge from their work. Upstream's actually deleting a lot of code right now, which is really helping our development. So as soon as this is done and passes the Go conformance test, this is going into the Go upstream. This is going to be an official Go port, and RISC-V will be a first-class architectural citizen within Go. So we're not quite there yet, but we're getting very close. I think it would not be at all over-optimistic to say within the next few months, you're going to be able to compile real Go programs and have them work on RISC-V.
Nobody running up to the mic? Oh, here we go.
Larry from Berkeley here. You say you have no silicon. Can you not afford a dev board, an FPGA dev board?
Well, we can definitely run on an FPGA dev board. Actually, we have RD boards, and now that the Freedom repository has been put up by Sci-Fi, we're excited about the prospect of getting to test on that. But Go really needs to run on in a managed environment. We're really looking for somewhere where we can run Linux, where we can run Go on top of Linux. There exist dev boards that you can run Linux on, yeah. So we can look into that as well. We would like to have real silicon though. That would be good. Yeah.
Adil from Intel. I was very curious about the slide you had about the TPU and how that relates to RISC-V. It's not. I know the question is not really related to Go, but is there some development on that with Google with using the RISC-V instruction set to develop a solution?
It's called RISC-V.
RISC-V.
Yeah, there's not much to say about that. It's just an example of Google investing in alternative ISAs and ways of computing.
Okay.
I'm Matthew from reconfigure.io. We do this Go synthesis onto FPGAs, and it was interesting to hear about the chunks that you have, like they're not running a runtime. Maybe we could look at synthesizing them as coprocessors beside.
Yeah, that's an interesting idea. You could have like a Go accelerator.
Yeah, yeah. That's
Yeah, I think we'd like to get the compiler just working to begin with right now, because it doesn't it doesn't actually compile things it doesn't compile non-trivial things just yet. So I think neither of us is a hardware engineer. I know I'm certainly not quite ready to dive into trying to re-implement parts of the compiler as an accelerator.
I'm a hardware engineer. I could help with that.
Oh, okay. Well, great.
Love help.
Yeah. Well, let's talk later.
Anybody else?
Rob Ferguson, Bit Science. Do you have any plans to target RISC-V 32-bit, or is it 64-bit only?
We will probably target 32-bit. We wanted to start with a single target, and we know, as has been said, Go is definitely a hosted language, expects to run on Linux. We expect that a lot of RISC-V cores that run Linux will be RV64, so we started with that. But there's no fundamental reason we can't add RV32 support with Linux.
Okay, thank you.
Is that it? All right. Thanks, guys.
You're welcome.